Then here the equation we can obtain. So what you could obtain is going back to the objective, we want to know the polarization inside the material by when the electric field is applied. And you could see this equation is the relation between the polarization and electric field. So if you can solve this equation, you can obtain the relation between the P and E. So that's what we are going to do. So here I'd like to introduce one of the property of the physical parameters of materials, which is susceptibility. You could see that the susceptibility is the coefficient of the E for P, right? So P is equal to the epsilon 0 chi and E. So this is a proportional coefficient for proportional coefficient of the polarization. So what we have to do is now we have to solve the Rorentz model given by the equation 8. And as we studied, we are more interested in the not the time domain, but in the frequency domain. So what we have to do is we have to Fourier transform the equations to solve this equation. So by Fourier transform, so the time domain is changed to the frequency domain. So it means that the P of t is changed to a P of omega, and E of t is E of omega. And the good things are, one of the good things in the Fourier domain is the time derivative is just changed to the scalar, so not the derivative one. So I omega p, and then second derivative is twice. You have to multiply I omega, which equal to minus omega squared times p. Right? So by using this, we can easily solve the equation like minus the first term equal and E squared omega. Right. And again, I would like you to remind that what we are interested is the relation between P and E, which is equal. It is the function of chi. So we can just divide P each term to obtain that P omega is equal and 0 E squared and 0 squared omega squared plus 2I omega gamma and E omega. Right. So just comparison between the definition and obtain the equation. You can easily obtain the chi form. So which is which is about 1. And you could see the denominator includes the imaginary number. So you can separate the real and the imaginary part of this equation, just some of the calculation, just making the sum of the calculations. And oh, by the way, this one is chi, original chi n, and then and there's just changing the sum of the numbers to and the imaginary one. Omega squared. And you can confirm the shape of this chi in the exercise section. So you could confirm how it looks like later on. Omega squared. Like this. So what we did is, let me remind you again that, so what we did is we started from the Rorentz model, and Rorentz model is converted in the Fourier domain, and we correlated the proportional constant between the electric field and polarization, and we could obtain the chi, which is susceptibility, and susceptibility is divided into the real term and the imaginary part of and you could see this is the function. These are function of omega. So omega is a frequency, right? So, and chi is the response, in a sense, response when you apply. If you have an object, if you apply the electric field, and this response is given by chi omega, right? So which means this chi shape is proportional to the most of the spectrum shape. So in this frequency region, so you can change the omega or nu or some, and you could see some of the shape. So this chi shape corresponds to the material response, meaning the spectrum for when the electric field is applied.